Welcome! Today, we're diving into the fascinating world of transformers, the groundbreaking AI models that power many modern language technologies. At their core, transformers help computers understand and generate human language, which is inherently sequential and full of context. Before transformers, models like RNNs struggled with long-range dependencies, forgetting information from the beginning of a long sentence. Imagine trying to understand a story where you only remember the last few words. This was the limitation previous models faced. Then came the transformer, a revolutionary architecture introduced in the 2017 paper, Attention is All You Need. At a high level, the transformer consists of two main parts, an encoder and a decoder, working together to process information. Let's first focus on the encoder. Its job is to take an input sequence, like a sentence, and turn it into a rich numerical representation. First, each word in our input sentence is converted into a word embedding, a list of numbers that captures its meaning. But words alone lose their order. So we add positional encodings, special numbers that tell the model where each word is in the sequence. These encodings are based on sine and cosine waves, cleverly designed to give each word a unique position signature. Now, for the core innovation, attention. This mechanism allows the model to focus on different parts of the input sequence simultaneously. Imagine you're reading a sentence. When you see a word, you don't just look at it in isolation. You consider how it relates to other words. In self-attention, each word embedding is transformed into three different vectors: a query, Q, a key, and a value, V. To figure out how much a word should attend to other words, we calculate a similarity score between its query and every other word's key. This similarity is often computed using a dot product, which essentially tells us how related two words are. To prevent exploding gradients during training, these scores are then scaled down by dividing them by the square root of the key's dimension. Next, a softmax function is applied to these scaled scores, turning them into probabilities that sum up to 1. Finally, these probabilities are used to create a weighted sum of all the value vectors. Words with higher attention scores contribute more. This weighted sum becomes the new representation for the central word, effectively encoding its context from the entire sentence. But why stop at 1? Transformers use multi-head attention, meaning they perform this attention process multiple times in parallel. Each head learns to focus on different types of relationships between words, like syntactic, grammar, or semantic, meaning connections. The outputs from all these individual attention heads are then concatenated or joined together. This combined output passes through a final linear layer to project it back into the desired dimension for the next steps. After multi-head attention, the result is combined with the original input using a residual connection and then normalized to stabilize training. This goes into a simple feed-forward network. Basically, two linear transformations with an activation function in between. And just like before, another residual connection and layer normalization are applied. A full encoder unit consists of these steps: multi-head attention, add and norm, feed forward, and another add and norm. Typically, the transformer stacks multiple identical encoder blocks on top of each other, allowing the model to learn increasingly complex representations. Now, let's turn our attention to the decoder. Its role is to generate an output sequence, like a translation or a summary, one word at a time. The decoder takes the encoder's output and the already generated part of its own output sequence as input. The decoder starts with its own masked multi-head self-attention layer. It's masked to prevent it from looking at future words in its output. This mask ensures that when the decoder predicts the next word, it only considers the words it has already generated, simulating sequential output. After its own self-attention, the decoder has a special encoder-decoder attention layer, also known as cross-attention. Here, the decoder's query interacts with the key and value vectors from the encoder's final output. This allows the decoder to pay attention to relevant parts of the input sentence while generating the output, aligning the two sequences. Similar to the encoder, the output then passes through another feed-forward network. And of course, residual connections and layer normalizations are applied after each sublayer in the decoder too. Just like the encoder, multiple decoder blocks are stacked to form the complete decoder section of the transformer. Finally, the output of the last decoder layer goes through a linear layer and a softmax function to predict the probability distribution over the vocabulary. The word with the highest probability is chosen as the next word in the output sequence, and this process repeats until an end-of-sequence token is generated. A huge advantage of transformers is parallelization. Unlike RNNs, which process words one by one, attention allows processing all words simultaneously. This parallel processing significantly speeds up training and inference, while the attention mechanism excellently handles long-range dependencies. The transformer architecture has truly revolutionized natural language processing, becoming the foundation for models like BERT, GPT, and countless others. From understanding complex queries to generating creative text, transformers are constantly pushing the boundaries of what AI can achieve in language. Thanks for joining.